Hello. Today we are going to learn about the method of images for a spherical surface, and then we will try to use Green's functions to see how we can generalize the problem. Let us recap what we have been doing till now. So we had this general problem where we have a volume V in space, and the volume is enclosed by a surface S. We know the charge density inside this volume, and we know the potential on the surface, which is basically our Dirichlet boundary condition. And we would like to find the potential for all points inside V. Okay. Using Green's functions, we previously saw if we can find a function g such that it satisfies the conditions that g vanishes on the surface and its Laplacian is minus 4 pi delta r minus r prime. If we can find a function g such that it satisfies these two conditions, then we can write the potential in the following way. We have a volume integral of the charge density times the Green's function minus surface integral of the potential times the gradient of the Green's function. So just to remind you, this integral is done for all points inside our volume V. Hence, we only need to know the charge density inside the volume, and this surface integral is done for all points on the surface S. Hence, we only need to know the potential on the surface as is given by our boundary condition and the charge density of our problem. Alright. So, in today's lecture, we will see how we can do this for a spherical surface. So, let us say we have a spherical surface S in space, and we can say that the center of the sphere coincides with the origin of our coordinate system. So we would like to find the potential in this volume V, which is basically outside the sphere. And we know the charge density in V. So basically we know the charge density for all points outside the sphere, and we know the potential on the surface S. So how do we solve this? So as we see from our previous slide, we would have to find the Green's function of this problem. And once we have the Green's function, we can solve the potential using the volume integral and the surface integral. So we would still have to solve the integrals, but however, at least we can find a way to express our potential in terms of these known quantities and the Green function. So as we had previously done, we will transform our problem to a simpler problem. So we will first try to solve a simpler problem where we have a spherical surface S and the charge density outside the sphere is just given by a point charge Q located at R1. So let us say the radius of the sphere is given by R. So what is the potential? So what is the potential outside the sphere? And we know the potential on the surface. Okay. So we have our charge density and we have our potential on the surface. We would like to find the potential in the volume V, which is basically outside the sphere. So using the method of images, we would again use the method of images, which we had used in the previous lecture. We would transform our problem to a similar problem where we have the same charge density and the same surface potential. So in this problem, we again have a spherical surface with the same radius R, and we have the same point charge Q because we need to keep the charge density in the volume V, that is outside the spheres, the same as the previous problem. So this charge density and this charge density have to be the same. And we also have to keep the boundary condition the same. So we would like to keep this square. So in the previous problem, let us just consider that this is 0, which was the case we had used in our planar surface problem. Makes the problem much easier. And so we would require to place an image charge somewhere inside the sphere so that this potential is 0. So basically we would have some image charge Qi located at position Ri. Let us write this here. So Qi is located at Ri. And what are Qi and Ri? If we have, say, any arbitrary point A on the surface, the potential at A in the presence of these two charges Q and Qi is given by Q by R minus R1 plus Qi by R minus Ri. and this has to be 0. So this equation is basically going to give us the image charge Qi and the position of the image charge Ri. So you can actually solve this equation for any general point Ra on the surface of the sphere, but here we would use trig to find Qi, to basically solve this equation. So the trick is that instead of considering a general point, you consider two very specific points on the sphere. So say this is Qi, this is Q and this is Qi. This is located at R1. This guy is located at Ri. And this is our center, which is also origin. So the two very specific points are the points B and this point B prime. So here you may ask one question, that why are we considering that the image charge is located on the line joining the center of the sphere and the point charge Q? So this can be basically just shown by symmetry arguments, that say the image charge is located somewhere else, for example here, then this point is basically equivalent to this point. These 2 points are basically the same with respect to our point charge. However, because we have the uniqueness theorem, we cannot have two solutions to our problem, right? The potential at some point here will be different if we have the charge here or we have the charge here, right? So the only way we can resolve this and follow the uniqueness theorem is if we have our point charge lying somewhere on this line. So basically it has to be inside the sphere, it has to lie somewhere inside this. So now what we are going to do is we will write this equation again. So we have the potential at Rb. We can write this as the potential due to the 2 point charges. So we have Q divided by R minus, so now we are finding the potential at Rb. So this is R minus Rb minus 1, and we have Qi Rb minus Ri. So now as all these points B, Ri and R1 lie on the same line, we can simply calculate or just find these distances by looking at our diagram. So we need to find this distance, which is the distance between the point R1 and the point B, which is given by this distance, and this can be found out by simply doing R1 minus R. So this is our R1 and this is our R. So we just subtract R from R1 and we get this distance. And similarly, we can find the distance between the point B and the point Ri by R minus Ri. And this has to be 0. And if we do the similar process for the point Rb prime, we'll get this equation. So 1 by 4 pi epsilon naught q. So now the distance between r1 and b prime will be r1 plus r, and the distance between ri and b prime will be ri plus r. So these are two equations with two variables, and this can be solved. But the important thing to notice here is that if we had taken our qi this way, let's say here we have q, if we had taken our qi somewhere here, we would still get, and if you can check this yourself, that we would still get these two equations. Check that we would get the same equations for qi and ri. So you can try solving these equations. I would just directly write the result. So we would get our image charge as minus q r by r1, and ri will be given by r squared by r1. Now the vector ri lies along the r1 vector, so we have r1 hat, and we can write this in this way. Alright, so our potential is now given by, so this is our potential outside the sphere. Let us say we kind of invert this problem. We know the charge density inside the sphere, and we would like to find the potential inside. Potential on the surface is again 0. Now this problem is exactly the same as the previous problem, because now if we want to find the image charge qi, if we go back to our previous problem, so qi is an image of q, which basically means that q is an image of qi. Alright, and if we check our equations here, you can see that this is symmetric with respect to ri and r1. So basically we can write the same equations. You can already see how powerful method of images is, because we can solve both problems at once, and now we know the potential inside the sphere is again given by the same equation, but here now we have just interchanged the image charge and the charge density, but the equation remains the same. So if we know the charge density inside the sphere and we have the potential on the surface, we can find the potential inside the sphere. And if we knew the charge density outside the sphere, we could have found the potential outside the sphere, which we just did. Now let us see how we can find the Green's function for our general problem. Remember that our Green's function must satisfy the condition that it vanishes on the surface. Potential outside the sphere. So first let us find our Green's function. So here we know the potential outside the sphere, and this function has to vanish on the surface because the potential on the surface is 0. So what we are going to do is we'll use the same equation, but we'll transform r to r prime because here r prime is on the surface, and we'll transform r1 to r. Alright, so now our image charge is basically located at r square by r square r. Okay, so our Green's function is now, so if we define our Green's function in this way, it is already obvious that by our definition this first condition is satisfied because this function, as we have seen before, vanishes on the surface S. But we also need to see if our Green's function satisfies the other condition, that its Laplacian is given by minus 4 pi delta r minus r prime. So this condition must also be satisfied. So let's see if our Green's function satisfies this. So in the previous lecture we had found out that the Laplacian of the inverse distance function is given by minus 4 pi delta r minus r prime, and here we will have 4 pi delta r squared r minus r. So here, as you can see, the derivatives are taken with respect to the primed coordinates. So the r is left unchanged. Hence here we simply treat the r as constant. So this is basically our image charge. Right? If we are trying to find the potential outside the sphere, our image charge is located inside the sphere. It can never be equal to r prime because r prime in our integrals is either on the surface S or inside the volume V. So basically r prime is either outside the sphere or on the surface of the sphere, while Ri is inside the sphere. So we can say that this delta function vanishes and we would have minus 4 pi delta r minus r prime, which is what we required. This Green's function works. So you can write the final potential as the charge density times the Green's function, as we have discussed before, minus the potential times the gradient of the Green's function. We know this from the problem. This is given to us. This is our boundary condition, also given to us. And now we also know our Green's function. This is our Green's function, and we can also find the gradient of our Green's function. As we had discussed in the previous lecture, what is the gradient of the inverse distance function? So this is just r minus r prime by r minus cubed minus. Alright, so you can just substitute this. So if you are given with any arbitrary charge density r and some arbitrary potential on the surface S, as long as this is like a spherical surface with radius r, you can find the potential outside the sphere using this equation where I found the Green's function. And so as we had discussed before, so if in this problem V was inside the sphere, we're going to use basically the same mathematical equations, and our Green's function will have the exact same mathematical form. However, now we just have to take care that our volume integral will be for all r prime inside the sphere. Alright, our volume is considered to be inside the sphere. We would have the same form of our equation, and now the volume integral will just be taken for all points inside the sphere. Alright, so let us see how we can use the Green's functions for some general problem. So let's say we have a spherical surface of radius r, and we have the following charge distribution. We have a charge q1 located at r1. We have a charge q2 located at some point r2. So q1 and q2 are located outside the sphere, and we have a charge q3 located at r3, which is located inside the sphere. So q1 and q2 are inside, and q3 is outside. And we can say that, say, this is a conductor. So this is our example which we are trying to show how useful the Green's functions are. So this is a conductor, which basically means that the potential on the surface is a constant, and we can take this constant to be 0. So here we have our problem. So we have to find the potential everywhere. So first let us solve this problem for outside the sphere. So what is our charge density outside the sphere? Charge density is due to these 2 point charges. So we have q1 delta r minus r1 and q2 delta r minus r2. And what is the potential on the surface? is basically 0. Alright? So, and our Green's function for the spherical boundary condition is given by, so this is our Green's function. So basically we can just substitute this into our equation for the potential. The potential on the surface S is 0 in our problem. So this term just vanishes. So here we have 4 pi epsilon naught, and the charge density is just the sum of two delta functions. The variable in our charge densities are primed, hence we have taken the prime coordinates in charge densities. If we have volume integral of a Green's function of a Dirac delta function times any arbitrary function, this basically gives us f of r is in V, right? So, and this is good for us because we are trying to find the potential inside our volume V. So here this R is inside the volume V. So you would have 1 by 4 by epsilon naught Q1. So you can replace the R prime with R1 and R2 over here. So we have one term where we have R1, and we would have another term where we replace the R prime with R2. So this is our potential outside, alright? And we already know the form of our Green's function. So basically just here, if you substitute R1 in place of R prime and R2 in place of R prime, you can get these two functions. So this is now solved outside the sphere. Inside the sphere, just need to know the charge density now. So the charge density is given by Q3 delta R minus R3, and the potential on the surface is again 0. So we can use the similar process. So again the surface term will vanish, and we would just have the volume term with a delta function, which is our charge density. So we have a charge density times the Green's function. And again using the property of the Dirac delta function, we would solve this integral where we would just replace the R prime with R3. This is inside the sphere. So we have the potential outside the sphere, and we have the potential inside the sphere. So now our problem is solved. Let us just summarize our solution. So inside the sphere, the potential is given by 1 by 4 pi epsilon naught Q3 GR R3, and outside the sphere, the potential is given by Q1 G R1 plus Q2 G R2. This is outside. And our Green's function is where our Green's function we have found out is given by 1 by R minus R prime minus R by R squared by R squared R minus. So we have solved our problem.